Good. Thank you for the introduction, Francisco.
Yeah.
Today I will be talking about Harveri, which is a small semi-autonomous precision tree harvester.
It's out of focus, probably.
Yeah, let's give it a shot. No. Okay, I just clicked through.
Is this not working? This right here should work.
It was working before, but
There you go. Yeah.
got it. Okay, thank you. So, what's the motivation behind forestry automation? So one thing is that it's been classified as 3D job, which means dirty, dull, and dangerous. So it's hard to get people to work in this field. It often involves traveling to remote locations, standing there for prolonged periods of time, which also doesn't make it any more attractive. And thus we're facing labor shortage, which one of the reasons contributing to this state is that most of the forestry operations are done using these big complicated machines, which then means it takes a long time to train your operators and to find them. So nowadays, kind of people are, the forestry paradigm is shifting and we're moving more towards precision forestry, which means that just decisions are made on much more kind of granular level. Often even on a single tree level, and then typically you would maybe scan your forest with some UAV, maybe even send humans then on the ground to refine this, get a bit more data, and then using some machine intelligence, we can like get the forest inventory and then present this on a smartphone or a cloud, where then some expert operator or even an algorithm can make decisions, what should we harvest next. So we believe that for this type of work, like smaller harvesters could actually be very beneficial. And the reason is, if you look at this video, like this small guy can really wiggle between the trees and it can really go and cut that single tree that the algorithm tells it to. However, the problem with these guys is that it's operated just using RC controller with like line of sight, as this guy in the orange jacket is doing. And then the human operator is basically exposed to all the elements and mosquitoes and anything else that could be in the forest, which means it's really hard to find people to do this. So what we would like to do then in this work is we would like to address this problem by introducing Harveri, and we would like to automate it kind of in 2 steps. Where first step would be we get the teleoperation going, which means we put necessary sensors there, we make a simulation, and then finally we teleoperate the machine. And then in the second step, we would like to have some semi-autonomy or maybe even full autonomy, something like in this picture here, where you just have one operator, maybe controlling multiple machines and just giving kind of higher level commands, as opposed to controlling each joint of the robot individually. So we looked a bit into what has been done, and so far we haven't found any existing work that kind of solves the complete problem. However, we found like people have looked into many subtasks that are required to solve this problem. So people have looked into which sensors do we need to estimate kind of the end effector pose, to estimate the state of the harvester crane. People have also looked into kind of open loop strategies for operator assisting. Creating forest inventory is like core technology that's already being commercialized. So there's a lot of work out there on that topic. And we've also found like automating bobcat machine for flammable material removal. So this basically means that for semi-autonomy of Harveri, we mostly build upon our previous work with harvester heap, which is essentially a Menzimuk M545 legged excavator. And in our previous work, we had like a sensor module, which then you take with a human operator to a forest, you collect some data, you build a map, and then we build like a global point cloud of this forest here on the left-hand side, which then this could be used by some algorithm to process this and make inventory. And also on the right side, we then built an elevation map, which was used for traversability estimation, which was then deployed on the robot for the mission. Before deploying stuff on the robot, we did some mission planning. Here, we just did, in our work, very simple GUI, where basically I was mimicking a expert human operator that would tell the machine, okay, go harvest these blue dots, which are like trees that are ready to be harvested. And then we took this sensor module and we put it in the back of the machine, put it in the localization mode, and then we told the machine, okay. So this is how it looked like. So here we were just giving kind of high level commands, go and harvest next tree, next tree, next tree, and then the machine plans an approach pose, drives to it, performs this scanning maneuver to build a local map such that we can correct for any inaccuracies in the localization, performs tree detection, and then it grabs a tree. And we also tested this exact same pipeline here in a different environment without any modifications with these sort of simulated tree trunks. And now what we would like to do is take this software stack from Heap and basically put it on Harveri. So Harveri is like a very small tree harvester developed by a Finnish company. It's 4.5 tons with payload of 1.5 tons. It's 4.2 meters as opposed to Heap in its like shortest configuration is 6.2 meters. They're comparatively, like the width is relatively the same. And then the payload, Harveri has only 400 kilos, where Heap has more than 4 tons at 8-meter reach, I believe. And Harveri only has 4-meter reach. So it's much smaller machine. So we first looked into what kind of sensors we might need to automate this guy. And the first thing that we kind of came up with is one of this kind of our main sensor setup, which is composed of a LiDAR camera and an IMU, which is then rigidly mounted together to basically facilitate the calibration. So you can calibrate it in the lab, and then you can just stick it on the machine. And then the way this is positioned on the machine is kind of near this boom here, such that whenever the crane swings left and right, this setup kind of moves with the crane. And we experimented, so we rendered first few positions in the Unreal image, in the Unreal Engine, and then we just refined it on the machine, just kind of iteratively. And the way this is positioned is such that the end effector tool is kind of always in the middle of the image. We also added 2 more LiDARs, one in the front, one in the back, which are just kind of redundancy modules for localization in case the main sensor setup gets occluded with some branches or tree debris. We also added the proprioceptive sensing, which then allows us to estimate pose of the arm and pose of the end effector. So here in red color, we use IMUs, which are then mounted as close as possible to the joint axis to minimize the centrifugal forces. And we use one draw wire encoder for the telescopic joint, because that one is inside the arm, so it's shielded from all the branches and stuff that might corrupt our measurements in the forest. And then this entire setup, so one joint is still missing, but assuming that we get this installed as well, this allows us then to know where the arm is in space. We also exchanged the actuators on Harveri. So we have these kind of actuator blocks where you have like a high precision servo valve. There's also an integrated microcontroller, which then runs this piston control, and then you can send the higher level commands from the PC. So you could maybe command position, velocity, and you can so it allows you to do relatively precise force control. And then all the kind of this piston control loop is really running on the actuator itself. For the computation, we use one of these Novo PCs, which has so it's nice because it has this passive cooling, so you don't have any dust problems in the machine. It also has some damping, which is which is also nice because we have like an engine which creates a lot of vibrations. And then we have Intel i7 and GeForce RTX GPU, which was basically chosen because of its hardware encoding and image decoding capabilities. So you should have as many decoders, as many streams you want to stream to the operator. So if you have 3 or 4 cameras, you need 3 or 4 decoders. And then the rest of the computing capabilities, so we are not using all of it at the moment, obviously, but in the future, we will probably run some segmentation or detection just to kind of enhance the operator's view. So now you might want to think like teleoperation with raw images, how would this look like? And here actually, if this video plays, okay, good. So here actually we have a very experienced operator. This was one of the very first tests that we did that is trying to grab this tree. And he just kind of reaches for this trunk and misses. And then he realized, okay, I have to drive a bit forward. And all of this he's doing kind of quite slowly and inefficiently compared to actually seeing the guy also operate the machine, which then went much faster. So then while creating teleoperation package, we kind of looked into which cues and AR elements can we add in this image to basically help him operate the machine. And then here, if this video plays, so here we have a very unexperienced operator, which is our master student Toon. So he's basically operating the same machine and trying to grab this. Nope. Okay. The video doesn't want to play, so you're just going to have to trust me that he succeeded in this task here. But basically what he was trying to do is, so he was trying to grab this tree trunk here, the close one, and then bring it to the pile of the other ones in the background. And then what vastly helped him are these like red dots, which is just kind of projection of your end effector on the ground. So know exactly kind of where you will touch. And also you have this red line here, which basically then tells you kind of what's your useful workspace, or like what's the reach of your arm. So basically you could just position the dot over the trunk, then drive until the red circle intersects the other trunks, and then just drop it there. And then the mesh that you see, the blue grid, this is just kind of elevation map, which is then projected into the image. So then we also want to basically port this, apart from teleoperation, we would like to design some semi-autonomy workflow for Harveri, and then we would do similar thing as heap, where you select one destination, the operator can then say, okay, just drive to this destination, scan, and then select which tree you want to grab. And so here, these are just some preliminary simulation results, where we have on the right-hand side is the simulation of Harveri in Gazebo. And then we have operator gives this purple dot as a goal point and says, okay, drive here. And now the path planner plans this red path, which basically avoids all the trees and respects the minimum turning radius of the machine. And then Harveri in simulated environment tries to follow that path. And so here are 2 more examples. This is actually a real forest, which we scanned, and then these red blobs, these are the trees, whereas white space is just free space. And so here are just a few more examples of planner planning and then machine tracking in Gazebo. We also looked into like these are just very rough prototypes. But basically, this is an interface for like tree detection, where then these white cylinders are simulated trees, and then the machine makes this swinging motion, again, builds local map of the environment, and then it will on the left-hand side present you, okay, these are the trees that I've detected. You can select one, click on it, and then tell, okay, grab a tree. So this is kind of going towards that direction of one operator just controlling multiple machines and giving higher level commands. So basically, to conclude, what we did in this work is we laid some first steps towards unmanned operation, because I guess teleoperation is not yet fully autonomous. So we looked into which sensors do we need to achieve this, and we ported a bunch of existing work from HEAP, like state estimation, AR elements, and elevation mapping, to Harveri. We also looked into semi-autonomous pipeline, also porting stuff from our previous work onto this machine. And so far we've tested arm controller, driving controller, planner, and tree detector. And what remains is to test all of these things on the machine. So future work, we still are missing some sensors that we need to properly integrate on the machine. Also design the proper rugged enclosures such that they survive some missions. And also then what we have to do is obviously a lot of machine testing, test all parts of the pipeline, planning, driving, tree grabbing, all of that, and also test the localization, which really needs to then work robustly in a pre-built map. Few things that we still have to develop is basically what do we do once we actually grab a tree trunk? How do we manipulate this tree, and then how do we put it maybe in this like payload container, I guess so to say. And we also would like to devise some control approach which would then reduce the swinging of this passive tool that we have at the end effector. So this brings me to the end. I'm a little bit over time. Sorry for that. Thank you very much for your attention, and big thank to Tun, who was a master student working on Harveri automation. So, questions? Or everything was clear? Yes.
Do you have to walk to another one to ask questions, or we?
You probably should, because there's some people.
All right. Well, first of all, thank you. Great presentation. It's great that people are actually trying to fix the whole pipeline and do experiments with real machine. One question would be, you're going to be able to record a lot of good data, like, human operators operating the machine with LiDARs, collecting data, cameras, and so on and so forth. Do you plan to record that data and make it available to the community so we can try to apply some machine learning techniques on that?
So good question. So far, we didn't think about it at all. But I think, so we do have one expert operator in the company that we're collaborating with. So it is a possibility, especially since some of my colleagues are looking into imitation learning and stuff like this. So it is a possibility. I can't tell you yes or no exactly.
I strongly encourage you, because I think, we'll discuss it probably in the panel, how lack of data is an issue holding back the community. And you already went through the pain of instrumenting a machine and operating it. I think you should record every bit of data and let the community decide what's useful or not. But I think this is a golden opportunity. Don't miss it.
Yes, thank you for suggestion. So if there are no other questions.
Yes, thank you for the presentation. I have a question regarding how well do you perceive tree with the LiDAR, and do you think using a camera would be useful?
So right now we have like a very simple tree detector, which if you had enough clutter and branches, it would fail. So we just do some Euclidean clustering, and then we look at these clusters and basically say, okay, you have to be gravity aligned. So we assume that trees kind of grow in the direction against gravity. But we're not right now not using camera, but I guess this is a bit out of my expertise, but I guess the state of the art are just some crazy CNNs for tree detection.
And what is the most limiting factor? Is it the perception or the control?
So at the moment, I would say the perception, and this is just based on our previous experience with heat, which actually, if you look at this video, like we deployed it. Unfortunately, we did our experiments during the wet season, and the machine was really wrestling with some quite nasty, muddy environment, but the control actually worked reasonably well there. With these fancy actuators that we have and like chassis balancing system, which tries to maximize the traction, this worked reasonably well. So in terms of kind of navigation, I think we're fine. I don't know what happens once we start manipulating trees, because we haven't done this, but we did have some issues with perception that basically our visual odometry would diverge, and then the whole LiDAR odometry would diverge because it was used as a prior. So there we definitely have some room for improvement.
Thank you.
So yeah, following in the traction topic, how is there what's the control strategy that you use? It was an MPC or model-based?
No, much. Yeah, it's model-based, but it's much simpler. So since you have four legs in contact, means you have kind of 1 degree of freedom redundancy. So we can control the height, the pitch, and roll of the machine. And then there's 1 degree of freedom, which we then just use. We run optimization. It's, I think, QP, quadratic program, which then just tries to distribute the force as evenly as possible on all 4 legs. And you have just a virtual force controller, which then calculates kind of what should be net torque on the chassis to pull me towards desired goal point, and then the optimization calculates, okay, which force distribution on each leg will achieve this. It's very simple.
Thanks. Any more questions? There are questions in the chat, Brian?
Just a comment that things were excellent.
Okay.
Yeah, so thank you, Edo.
Thank you.